they asked me to give an overview or introduction to quantum computing, and that's what I'd like to do. And basically, quantum computing, as you know, has a lot of jargon and words and things that conceptually I think you understand, but sometimes we just don't know the vocabulary words. And so that's the goal of this, is to help to introduce what quantum computing is, what are the technologies, what are the words associated with it, and many of the concepts we'll see here today in this talk you'll see throughout the next 3 days. But before I get going, let me start with the video. In fact, it's the first video of the MIT X Pro professional development course. It's 160 videos, 4 weeks long by 4 courses, so a total of 16 weeks. And I'll talk more about it after the video. We hear about quantum computers nearly every day in the news and in the popular press.
That's what's exciting about quantum computing, and that's what we're doing.
It's said that quantum computers will solve certain types of problems, ones of tremendous importance to humankind, and problems that today are practically prohibitive or maybe even impossible to solve with current computers. We hear about pharmaceuticals and drug discovery, gaining a better understanding of new materials like high-temperature superconductors and how they work, new methods for machine learning, artificial intelligence, optimization problems, financial services and technology. Quantum computers will even challenge and change the way we securely communicate information. It certainly sounds like a fantastic and exciting future, which leads us to a few fundamental questions. What exactly is a quantum computer and what's it good for? More importantly, when will we have one?
Quantum computers are not just smaller, faster versions of classical computers. They're fundamentally different.
Where in the digital computer world, a bit, which is one basic element of information, is a 0 or a 1, nothing else.
In a quantum computer, you can have a quantum bit or qubit that's in a superposition of 0 and 1.
We can design it, we can actually control it. We're actually engineering and manipulating quantum mechanics.
So when we'll have a quantum computer is a very interesting and nuanced question, and the answer will therefore be kind of finicky.
We've been saying quantum computers are 10 years away. We've been saying that for decades.
Depending on your definition, we already have quantum computers. They're just small.
Within my lifetime, I believe, and I won't say how old I am.
This is not decades away or 100 years away. That quantum age has now come.
Quantum computers aren't simply faster, smaller versions of the conventional computers we have today, nor are they another incremental step in the evolution of Moore's law. Rather, quantum computers represent a new, fundamentally different computing paradigm, one that carries tremendous advantage for certain types of problems of importance.
Quantum computing could really transform industries where there are significant optimization problems. You've got a lot of discrete or binary decisions to make to figure out, do you do this first or that first? This is where we shine.
Another way to understand the difference between classical and quantum computer is if you look at quantum systems of quantum simulation.
The quantum processor is a suitable tool for modeling other quantum systems.
Biomolecule systems, tons of systems that we use, material systems, work based on those quantum mechanical properties.
You kind of need a quantum machine in order to simulate quantum effects. When we can manipulate individual molecules and understand what's going on in those molecules, how they bond, then we'll be able to have a really good handle on generating new things, novel materials that might be very useful.
Still, we're just at the very beginning of quantum computing development, assembling and testing the first prototype processors. It's a bit like being in the 1950s at the dawn of transistor-based computing. And just as integrated circuits led to an information processing revolution last century, driving economic growth and productivity, many people today believe that quantum computing will have a similar impact this century.
Quantum computing and quantum algorithms present fundamentally new programming and algorithm design paradigms. How do we fundamentally unlock new ideas in computing?
We're still learning a lot about how to improve the individual components as well as connect them together.
That's part of the fun. That's where I'm there to see what can we do to enable that increased complexity and functionality of these qubits.
We're really here at the very beginning, and I just find that tremendously exciting.
Yeah, so indeed, it is the very beginning, and we're not very far along in this marathon, if we want to think of that, maybe in the first mile. But to understand how this will unfold going forward, of course, we can't see that, we don't have a crystal ball, but what we can do is go back and look at the history of classical electronic computing over the last 100 years or so. And that started with the vacuum tube in 1906. And it was used for radio transceivers for decades. And eventually, by about 1946, we had the first vacuum tube-based computers, which I'm sure you've heard of, called ENIAC. Now, around that time, in 1947 at Bell Labs, the transistor was invented. And within about 10 years, we had the first fully transistor-based computer. It was called TIXO, or TX0, developed at MIT and Lincoln Laboratory. But it didn't look anything like the computers we have today. These were soldered together transistors and a magnetic core memory, and very different than the integrated circuits that we now know and use. The integrated circuit came around 1958, and it was another 20 years or so before we had the first integrated circuits from Intel, like the 4004 and the 8008, et cetera. And then it was another 20, 25 years to get to the Pentium Pro with millions of transistors. And then another 20 years to get to the multi-core processors and GPUs that we are now using today with billions of transistors. And from where we stand today, looking back, it's fully, well, in excess of 100 years of development to get to this point. Now, we can compare with that quantum computing, and it's much more nascent. In the early 1980s, Richard Feynman and others suggested that if you want to simulate a quantum system, you should use a quantum system to do that, because quantum systems are notoriously hard to simulate. Well, why? Well, they have lots of atoms, and they have lots of degrees of freedom that all need to be kept track of, and it just gets too large for classical computers to do that. So people took about 20 years thinking about what kind of algorithms can I run on a quantum computer. And so we'll go through some of those algorithms in a moment, but in the mid-90s, people like Peter Shor and Eddie Farhi and Nishimori from Japan, Lev Grover at Bell Labs, came up with the first quantum algorithms. Now, they didn't have any hardware yet to run it on, but they knew that if we could build those computers, we could do some amazing things. And then around 2002 was the first demonstration of Shor's algorithm, which, as you know, applies to cryptanalysis, factoring large numbers into its prime. And in 2002, we factored 15 into 3 times 5. It showed that the algorithm worked. Clearly, it's not at scale yet, but it showed that the algorithm worked. And then another 15 or 20 years to get to where we are today with few qubit processors, 20 qubits, 50 qubits in the cloud, and of course, Google's recent demonstration of quantum supremacy. So what's the takeaway message? The point here is that quantum computing is transitioning from scientific curiosity to technical reality. That is happening right now. But we know that advancing from fundamental discovery to useful machines takes time, and it takes engineering. And the other thing that we can perhaps draw from this is you have to be in the game to play, even from an early stage. Right? Maybe it's no surprise that many of the companies today building these multi-core processors and the processors that we have in our computers were in this game for a very, very long time. So what are some of these applications that quantum computers are good for? And how do they do it, the approaches? Well, the most powerful quantum computer is a universal fault-tolerant quantum computer. This is a computer that can run any quantum algorithm, and it can run any classical algorithm for that matter. But it often does not perform better than a classical computer for most of those classical algorithms and even some of the quantum ones. But for some of them, such as Shor's algorithm shown here, it exponentially outperforms classical computers. And what I show here is the processing time versus the bit length of an RSA key, an encryption key. And you can see that the magenta skyrockets as you increase the key. If you're dissatisfied with your level of security, double the length of the key, because it becomes exponentially harder for a classical computer to crack that code. But for a quantum computer running Shor's algorithm, this will be polynomial in time. And that's very efficient, exponentially faster. Now, if it's just cryptanalysis, that's of course very important, but that is not necessarily commercializable. So rather than that, of course, we're thinking about database searching, linear equation sampling, optimization problems. For this type of universal computer, quantum speedup exists. Dramatic quantum speedup exists over known classical algorithms if we can build this computer large enough for important problems. And that's the furthest off, 20 or 30 years. I think in the nearer term, what we're looking at is digital and analog quantum simulators. We're talking about quantum chemistry, drug development, material science. These applications may not even be fully error corrected. They may be error prone, but we still may be able to do something with them. And again, for some of these problems, quantum speedup exists over known classical algorithms, but it's only useful if we can build a quantum computer large enough for important problems. And the third type of quantum computer is called a quantum annealer, and this is different than the former two. Quantum annealers focus explicitly on optimization problems. And it's not known today whether quantum annealers will afford a quantum speedup or not. It's not theoretically proven that it will, nor is it theoretically proven that it will not. But optimization problems, as you know, are ubiquitous. Everybody's trying to optimize something, whether it's your bottom line, a plan, a route, satellite tasking. And because it's ubiquitous, it's very important that we find out if quantum annealers can support quantum advantage, and if so, in what way. So how is a quantum computer different than a classical computer? Just 2 slides or 3 slides on how this works. So we know that a classical computer is based on a bit, a transistor. It's in state 0 or it's in state 1. That's it. A quantum computer is different, though. A quantum computer, we can think of that block sphere that Matt referred to earlier. Think of it as the planet Earth. And the North Pole is state 0, and the South Pole is state 1. And if you're at the North Pole or the South Pole, you're a classical object. But you don't have to only exist at those 2 points on Earth. You can exist anywhere on the surface of the Earth. And when you're anywhere but the North and South Pole, you're in something called a superposition state, which carries aspects of both 0 and 1 simultaneously. This is a manifestly quantum mechanical state. And so what it means is that quantum computers rely on encoding information in a fundamentally different way than classical computers. So what's the consequence of superposition? Well, in a classical computer, if you want to compute a function of some number, you want to get an answer to some number, you put that number into the computer, and it calculates the function and gives you an output. Now, if you want to do it to another input, you have to take a separate input, put it into the computer, and get an output. And this is called parallelism. You can either do this by having multiple copies of the machine and do it in parallel, or you can do it sequentially in time. But the point is, if you have n bits, you'll have 2 to the n. That's an exponentially large number of states, and you can only work on them one at a time. And so it's exponential in time or exponential in space. A quantum computer, on the other hand, can take those 2 to the n different components and put them all into one superposition state simultaneously. And this leads to a manifestly quantum effect like quantum parallelism or quantum interference, and this is what underlies the exponential speedup that we see in a quantum computer. So given that, how does an algorithm unfold or work? Well, let me say that it in many ways is just like a classical computer, in the sense that classical computers work on bits and gates. So 1-bit gate, 2-bit gate. And with a handful of those, an AND gate, a NOT gate, etc., you can perform any Boolean logic that you wish. You can perform any classical algorithm. And similarly, a quantum computer has a handful of 1-qubit and 2-qubit gates. And with a handful of those, you can do any quantum logic. And this is basically how it works. So you start with an input state, which is a massive superposition state, carrying aspects of all 2 to the n components. And you put this into your computer, and there you run an algorithm. And so the types of things that you'll do is you'll apply a single qubit operation to 1 qubit. But as you see in the illustration here, it affects all states, or all aspects of that state simultaneously. So 1 qubit, 1 gate, but in fact, it's changing everything inside this state space. That's followed by quantum interference. And what that does is it changes the weighting coefficients in front of these various aspects. Now, there's another type of gate called a 2-qubit gate, where depending on the state of qubit 1, I'm going to perform an operation on qubit 2. And that's followed by, again, quantum interference, which modifies these coefficients further. And the goal of an algorithm designer is to ensure that by the end of the algorithm, almost all of the weighting is in one of those aspects. In this case, the 0, 0, 1, beta prime equals 1. And all the other ones are 0. Because when we make a measurement, we have an exponential slowdown. We are classical beings, and we measure things in a classical sense, and we can only get one of these states at the output. But we get them with a probability that goes as this magnitude squared. So with probability 1, we will get the right answer. So that's the goal of an algorithm designer. Okay. So here are some algorithms that we have listed on the left. I won't read through the whole slide, but quantum simulation, factoring, sampling solutions to linear systems of equations, optimization and search. And you can see the classical and the quantum time, and basically what you see is that the quantum time is, in general, either exponentially or sub-exponentially faster. Okay. So there's a lot of promise here, but to realize this promise, we need to engineer quantum systems that are robust, reproducible, and extensible. We need to make quantum computers that are large enough to run these algorithms on real problems that we have. And why don't we have that today? Well, it comes down to two times, coherence time and the gate time. So let's take them one at a time. The coherence time is the lifetime of the quantum mechanical properties of the qubit. We can take a qubit, we can put it in some position on the Earth at time t equals 0, and it interacts with its environment, and over time what happens is that state, represented by psi, becomes blurrier and blurrier, and eventually it's lost. Now, the qubit is still there, it's in some state, it's just unknown to me as the algorithm designer. And this lifetime, this duration of time that the qubit remains viable is called its coherence time. Now, the second time is the gate time. We do these 1 and 2 qubit operations. How long does that take? Faster is better. Because the figure of merit is how many gates can I apply before my quantum bit loses its coherence, its nature, right? That's the figure of merit. And so with that, we can compare different qubit modalities that are being investigated today as platforms for quantum computing. And what we're plotting here is the number of operations before an error on the vertical axis. That's the number of operations in the coherence time. And then the gate speed on the horizontal axis. Now, number of operations, we call that gate fidelity. It's basically 1 to 1. If I have 100 operations before an error, that's basically 99% fidelity, etc. And this red dashed line that you see here, this is called a threshold. And what the threshold is related to quantum error correction. If the qubit quality is above this threshold, then adding redundancy, actually adding more qubits to the problem, will actually improve the overall performance of the computer. If you're below this line, then adding more qubits just makes things worse. That's what we mean by a threshold. And this happens to be the most lenient threshold for one type of error correction protocol. There are many. Okay. And the best performance, of course, is in the upper right. So there are a number of technologies that have demonstrated 1 qubit gates. So shown here are phosphorus-doped silicon and silicon MOS dots. And then there are a number of other technologies which have demonstrated what we call a universal set of gates. That's both single and 2 qubit gates that you need to implement quantum logic. And those include superconducting qubits, trapped ions, NV centers, neutral atoms, and silicon quantum dots. Now, just to give some perspective and show a few pictures here, these are folks at MIT and Lincoln Laboratory, my colleagues who are working on trapped ion research. And here are a number of people, including myself, working on superconducting qubits. And I would say these are the 2 leading candidates today for building a quantum computer. And if you ask me, what are we researching? Trapped ions are trying to make higher fidelity 2 qubit gates, and they're trying to run their qubits faster. And superconducting qubits are already pretty fast, so we're just trying to improve the single and the 2 qubit gates. And the speed matters. And the reason that speed matters, you might be thinking, okay, well, why do I care if the quantum computer is fast or slow? Because what we care about is this problem took the age of the universe on my classical computer, and I can do it efficiently on my quantum computer. Well, that's true. But if it took me a day to run it on my superconducting quantum computer of the future, and I know that ion traps, let's say, run 1,000 times slower, all else being equal, it'll take 1,000 days on a trapped ion quantum computer, and clearly that's not a human timescale. So even though we get this exponential speed up in many cases for quantum computing, we still care about the human timescale, what we call the prefactor. That still matters, right? And so we want these to run as quickly as possible, and the research is in that direction. A few other modalities here are neutral atoms, as well as NV centers, and again, colleagues at MIT, Lincoln Laboratory, as well as collaborators at Harvard, just to give a flavor of who's doing what in the field. So there are many candidate technologies under development to realize the promise of quantum computing. And which one is going to win? Well, of course, maybe multiple, right? If we look back at the history of classical computing, there wasn't one technology. It wasn't vacuum tubes now and forever. It emerged and evolved over time. And in fact, even within the transistor family, we started with bipolar junction transistors, went to emitter-coupled logic, eventually on to CMOS, etc. So, of course, there's a lot of activity going on worldwide if we take a step back for a moment. And what I've listed here is mostly the government efforts across the world. I won't read them all, but you can see that there are some very large numbers being invested there. But what's really changed, to my mind, over the last 5 years is the large numbers of companies that are now getting involved because they see the impact of quantum, or they can foresee the impact of quantum on their future bottom line. And when I look at this, I'm very excited because I see that this is transitioning from the laboratory to the real world. But I also know as a professor at MIT that we need to continue fundamental research. It's important to do engineering. We need to do that. But we also need to understand what is that engineering and what are the rules and what are the abstractions, and we still need the quantum science. And so it's in this context that we've started a Center for Quantum Engineering at MIT. And I'll just tell you briefly about that now. So this center was established to basically, it was dedicated to the academic pursuit and practice of quantum engineering with the goal of accelerating practical application. And as part of this, we need to define what this new discipline, quantum engineering, is. It's not engineering. It's not just quantum science. It's somehow bridging these together to build these systems. We need to educate tomorrow's quantum engineers. We need to fill that pipeline. And in fact, the professional development course that I drew that video from is one of our efforts at MIT to do just that. We're also partnering with industry and government, but in particular, we have an industrial membership or consortium. Be happy to tell you more about that. And basically, we want to maintain and advance not just MIT, the Institute's role, but our nation's role in this important space. So there are a large number of members. I won't read through them all here. And this is just a partial list, as many as I could fit on this slide. And in the last year, since we've instantiated this center, we have developed a number of partnerships. One is with the Laboratory for Physical Sciences, graduate fellowships, sponsored research programs, and curriculum development. We also started this industrial group that I mentioned. And there it's about engagement with students and faculty, outreach, special events, recruitment opportunities. And then third is this MIT X-Pro professional development course. This was sponsored by IBM, and it's 4 courses, 4 weeks each, looking at the fundamentals and the practical realities of quantum computing. And it's really targeting people who are already in business, industry, government, who just need to quickly learn what is quantum, why is it important, what are these terminology, what do they mean, things like that. And so as I get to the end of the talk, what is quantum engineering, right? What is this new discipline? Well, it's clearly going to draw on many of the disciplines we already know from a university setting. For example, the computer science department, electrical engineering department, mechanical engineering department, chemistry department, biology department, and physics, mathematics, right? Science, School of Science. But it's also drawing on classical engineering like analog and digital circuit design, control and DSP, materials and fabrication. All of this is important. And all of it we know a lot about from the last 50 to 100 years of classical computing development, but it needs to pivot. And that's the new discipline, quantum engineering. It needs to pivot so we can build these test beds. We have to understand what the abstractions are to take us from the fundamental quantum physics to the rules of thumb that engineers can use to build systems so that people can design algorithms without knowing what's going on in the guts of the quantum computer. And all of this, I would say, is within the purview of quantum engineering. And so with that, let me just summarize, quantum computing is happening, absolutely. As Matt mentioned, there's a lot of hype in the field these days. I think that's reflective of the fact that there is something real here, that it is happening. There's probably too much hype. We have to watch that. In this context, we've started the MIT Center for Quantum Engineering. We have the quantum computing MIT X-Pro development courses, and the Industrial Consortium. I'd be happy to tell any of you more about these topics, but now I'm at the end of my time. So thank you for your attention. I think we have time for maybe 2 questions. Stunned silence, yes.
Could you comment on any
Yeah, so the question was, development or, comparing to, say, the development of analog computing and how quantum computing compares with that. Is that the question? Yeah. So, in fact, quantum computing looks a little bit like an analog quantum computer in the fact that, you think of this planet Earth and you say, well, I could be anywhere on the surface of the Earth, and that is certainly an analog quantity. It's not discretized. But in fact, because when we make a measurement, we project ourselves along any axis that we draw on this planet Earth. So say the axis between the North and the South Pole. When I make a measurement on my qubits, wherever I am on the Earth, I get projected onto that value and then proportionally to the North and to the South Pole. So it's probabilistic. And it's based on that we can discretize errors, and we can do quantum error correction where we make measurements like the parity checks in classical error correction. We do them in quantum error correction. And this parity basically projects us into an error state or no error state. And that's very interesting because when you make a measurement, you collapse the quantum information, and you think, well, then how could I ever make a measurement on a quantum computer? But it depends on the question you're asking. If I measure 0 or 1, of course, then, okay, game over. I've projected out the quantum information. But if I only ask the question, was there an error or no error, I didn't really learn anything. Let's say there was a bit flip. I knew 0 became 1 or 1 became 0, but I never knew which was which. And to correct it, I know I just need to flip the bits back. And so that's, in a nutshell, that's how quantum error correction works. And it's because of this that quantum computing is not quite analogous to analog classical computing. Maybe one more? Yes?
In the sense that we're trying to solve these general engineering problems around the technology, at what point does it move from general engineering problems into maybe industry-specific engineering problems? And are we there yet?
Yeah, so the question was, when does this move from, say, general foundational engineering to industry-specific systems, solving problems engineering, and are we there yet? I think that we are starting to move there. There are definitely tasks that have moved into an industrial space that I, as a professor with my grad students or my team at Lincoln Laboratory, that we're not going to address those problems, that these are problems that are best suited to industry as well, I should say. But on the other hand, because we're so early in this game, there is no textbook called quantum engineering. I should be careful. Maybe there is, but the point is that if there is, it hasn't been around for very long, and we need to write more of them, right? And so I would call this foundational engineering, much as we have foundational science, basic engineering, to develop these abstractions and feed in. So I see both of them as important. The industrial setting, it is happening. 5 years ago, we were both, in fact, I would say academia, government labs, and industry, we were all in the same lane, trying to do exactly the same things, stepping on each other's toes. But that is starting to clarify itself now. There's definitely an industrial lane, there's a government lab lane, and there's still a very important university lane. But thank you for the question.